Hi there. We're on day 6, so let's go ahead and get started. What we're looking at today are examples in which um, we are allowed to repeat the objects that we have selected. That is, once we have chosen an example of something, um, we can choose it more than once, but the order in which we make the choices does not matter. So, um, order does not matter. And we can repeat choices already made. Okay? So in our example here, we're in a soda warehouse that has vast quantities of these sodas: Coke, Diet Coke, Sprite, Mr. Pibb, and Fanta. Customers can create 12 packs in which they can freely mix and match from among these sodas. How many possible 12 packs are there? So we're assuming that the contents are important. So, for example, 10 Sprites and 3 Fantas is a different 12 pack from 9 Sprites and 4 Fantas. But in which the order in which we package the contents is not important. Okay. Um, so I want to talk about a couple of ineffective strategies that don't work. So this doesn't work. We have 1, 2, 3, 4, 5 different kinds of sodas, and 12 blanks. Put them in the box. If I say that I have 5 choices for each blank, and say, not 5 factorial, 5 raised to the 12th, um, this takes the order into account. This would work if order mattered. And let me see if I can sort of justify what's going on here. If we just do 5 to the 12th, I might choose Fanta for my first soda, and then I'm free to choose for the second soda, so I might choose Sprite for the second soda, and I might choose Mr. Pibb for the third soda, and then I might choose Fanta for the fourth soda. But if I made the same choices in a different order, um, Mr. Pibb first, and then 2 Fantas, and then a Sprite, then I'm creating the same arrangement, just in different orders, and all those different orders are being counted in the 5 to the 12th. And so um, that strategy turns out to overcount. It counts all the different possible arrangements. Okay. Um, so then another strategy that doesn't work then would be to try to take 5 to the 12th and then divide it by something, by the number of different ways we can rate the same arrangement. And the problem is that this is just super complicated. Um, and here's why. If my arrangement contains, um, let's say, 11 Diet Cokes and 1 Sprite, then there are 11 factorial different, not 11 factorial, just 11 different ways we can arrange this. Actually, there are 12 different ways we can arrange this. because the sprite could go in any one of these 12 spots. And once we've chosen which spot the sprite goes in, the Diet Cokes would go in the rest of the spots. Um, but if my arrangement consisted of, say, 10 Diet Cokes and 2 sprites, then there are 11 choose 2, which is 55 different ways of placing 2 sprites in here. Um, and so the number that we have to divide by depends on the particular case we've chosen. Um, and if instead of having 10 Diet Cokes and 2 sprites, I had 10 Diet Cokes and 1 sprite and 1 Mr. Pibb, then I have to think about the arrangements. Does it matter whether if the sprite goes in this spot and the Pibb goes in this spot, or the other way around? And it turns out that we would have to divide for that as well. And so now our denominator is 110. That what we would have to divide by is different for every different arrangement that we get. And so um, the denominator would be something that would involve a bunch of cases, and um, counting all those cases manually is just a nightmare. And so what we need is a brand new strategy. And so here's the idea that we're going to follow here. Let's imagine that we had a robot. So here's my robot. And the robot has a little, two little grabby things. In one hand, the robot's holding bag to put the cans in, and then the other hand is picking up the cans. And the robot I didn't know that very well, but that's okay. Um, Stands in front of an aisle in which there are cans of Coke, cans of Diet Coke, cans of Sprite, cans of Mr. Pibb, cans of Fanta. And the robot reads instructions in binary. And the instructions are, if the robot reads a 1, pick a can from the current bin and add it to the bag. And a 0 means move to the next bin. And at the end of the bins is a station where the robot can drop off the bag once the order is complete. Um, Once this robot has advanced to the table, the robot will automatically drops bag at the finishing table and resets. So let's look at what might happen here. The robot is standing right now at the Coke bin. And let's say we want to create this particular arrangement. Um, one Coke, 3 Diet Cokes, 2 Sprites, and let's see, that's 6 sodas so far. I said 2 Sprites. I don't know why I wrote a P for that. Um, 2 Sprites, no Mr. Pibbs, and then 6 Fantas. Okay. All right. So how would we code this in a set of instructions? We would pick 1 Coke, so that's a 1. Pick a can from the bin and add it to the bag. Then move to the next bin. That advances the robot to the Diet Coke bin. Take 3 cans off of the Diet Coke rack and put them in the back. Advance to the next bin. Now we're at the Sprite bin. Take 2 Sprites. Advance to the next bin. Now we're at the Mr. Pibb bin, but there are no Mr. Pibbs to grab. So advance to the next bin and then grab Fantas. There are 6 of them to grab. So 1, 1, 1, 1, 1. The bag is full, and since the bag robot is already at the end of the row, we can put the bag on the finishing table and complete the order. Okay. Let's look at a different order. And I did not give myself a lot of space here, but let's try this order. What if we wanted just 5 Diet Cokes and 7 Sprites? Okay. So how would that order look like? The robot is starting at the Coke bin, but doesn't buy any Cokes. So 0 takes the robot over to the Diet Coke bin. And then the robot will take 5 Diet Cokes. 1, 2, 3, 4, 5. Then the 0 moves the robot to the Sprite bin. And then 1, 2, 3, 4, 5, 6, 7 Sprites. The bag is full, but the robot is not over at the finishing table. And so to get the robot to the table where the robot can automatically drop the bag off, we have to advance the robot to the Sprite, not from the Sprite to the Pib, and then from the Pib to the Fanta, and then that's where the end table is at the row. Okay. A correct order will have 12 ones because the robot has to put 12 sodas in the bag. And 1, 2, 3, 4 zeros. Wants to move from the Coke bin to the Diet Coke bin, wants to move from the Diet Coke bin to the Sprite bin, wants to move from Sprite to Mr. Pibb, and then wants to move from Pibb to Fanta. And we have to put those at the end of the order to get the robot to the end of the table. And so our protocol is any string of 16 bits, 12 plus 4, that has 12 ones and 4 zeros should be a correct order. Okay. So let's see if we can make this work here. Okay. I'm going to go over here and erase the stuff that doesn't work, and let's just try expanding on this idea here. Any string of exactly 12 ones and 4 zeros is a valid order. For example, if we did, let's look at this string. 2 zeros at the beginning, 6 ones, 1 0, 6 more ones, and then 1 more zero. That's 12 ones and 4 zeros. What is that instructing the robot to do? Skip the Cokes, skip the Diet Cokes, take 6 Sprites, skip to Mr. Pibb, take 6 Mr. Pibbs, then skip to the Fantas. Don't take any Fantas because there's no ones after that last zero, but we're at the end of the table with a full bag. Okay? Any string of exactly 12 ones and 4 zeros is a valid order. 2 different strings means 2 different orders. There is no other string that would get me 6 Sprites and 6 Pibbs. If I put any ones over here, I would be grabbing some other kinds of sodas. If I put an extra 0 over here, I would overshoot the Sprite bin. And so I would have to start with 2 zeros. I have to have 6 ones to pick the 6 Sprites. I have to have a 0 to get to the Mr. Pibb bin. I have to have 6 ones to pick up all 6 Pibbs. And then I have to have the closing 0 to get me to the end of the row where the finishing table is. And so this strategy here of combining ones and zeros to form a valid order counts every order and doesn't count any order twice because different strings represent different orders. And so how many ways do we have of taking 16 bits and picking 4 of them be zeros? That would be 16 choose 4. Okay. The number of bits is equal to the size of the pack plus the number of different cans of sodas minus 1 because we only have to instruct the robot to skip from one box to the other. And so if there are 5 different boxes, we need 4 zeros to do this. So there are 12 ones and 4 zeros because there are 5 different kinds of sodas. And then we choose which ones will be zeros. We could have also chosen which ones would have been ones. 16 choose 12. We've mentioned this before. This is a symmetric identity. Choosing the 4 zeros or the 12 ones both results in the same value. Okay? All right, so let's try some other examples. A donut store carries 5 varieties of donuts: chocolate, maple, Boston cream, powdered, and jelly filled. Okay? Chris wants to buy 8 donuts from the store. So we have our robot here. The robot is holding a bag and then is picking donuts and putting them into the bag. There you go. I can't draw, but that's okay. An order is finished when the bag is full and the robot has reached the table. And so in order to buy 8 donuts, we need 8 ones. buy 8 donuts. And 1, 2, 3, 4 transitions because there are 5 kinds of donuts. 4 zeros, 5 kinds, which means 5 minus 1 is 4 transitions. That's a total of 12 bits total. And so we have 12 bits in our order, and we have to choose 4 of them to be zeros. The total number of bits how many zeros to choose. Okay. All right. We have this algorithm for solving this problem by converting the actual selection process into something in binary that we can count. And we've never used this kind of strategy before, but this strategy works for these specific problems where the order doesn't matter and we can repeat choices. Okay? All right, so let's try this again. The number of ways of choosing R objects from N types of objects is, here's the way the theorem is stated in a book. These are the number of objects that we're buying. These are the number of types, and N minus 1 is the number of transitions between the types. And then we either choose how many ones or choose how many zeros. In this case, they're choosing how many ones because we're choosing the number of objects we're actually building. And this works also. So the number of objects we're buying, N minus 1 is the number of transitions. And then we choose either N minus 1 or we choose R. It doesn't matter which. Okay. So we do have a formula for the base case, but again, I think memorizing the formula and not the strategy is a bad tactic. Okay. All right. So once again, we have 5 different kinds of objects here: red, green, yellow, white, and black jelly bean. And we want to select 20 of them. So this time we need 20 ones and 4 zeros. We need the 4 transitions between the different kinds of jelly beans. And so that's going to be a total of 24 bits. And so that means we'll have 24 bits in which we have to choose 4 of them to be zeros. Okay? But what if we have to select at least 2 jelly beans of each color? How does that complicate the problem? So in this case, if there is a must select condition, we will pre-fill the bags with that requirement, with 2 reds, 2 greens, 2 yellows, 2 whites, and 2 blacks. That satisfies the requirement. But now the robot only has to pick 10 more jelly beans. Ten more jelly beans. And so we'll have 10 ones and 4 zeros. And that's 14 bits, choose 4. Okay. That is, if we have to have 2 jelly beans of each color, just to pre-fill the bag with that requirement, and then let the robot do the robot's thing for the remaining 10 jelly beans. Okay? We don't have to change the algorithm, we just pre-fill the bag. And so that would be the answer for part 2. All right? Let's keep going. 2 lottery systems are proposed. In the first system, players select 6 different numbers from 1 to 50. In the second system, players select 6 numbers from 1 to 45, but may select any number as many times as they want. And so this one has repetition. Okay? So let's look at the first sentence, first system, sorry. There's no repetition. And so this is not a robot problem. This is just that there are 50 numbers to choose from, and we have to pick 6 different ones. Okay? This is not a robot problem. Since there's no repetition. There are 50 different numbers to choose from. Players have to select 6 of them, so that's just 50 choose 6. In the second system, we have to have 6 ones because the player is selecting 6 numbers. But there are 45 numbers to choose from, which means there are 44 transitions. And so there would be 44 zeros. I'm using the ones and zeros strategy here because there is repetition in this case. And though there are a total of 50 bits, and so we get 50 choose 44, but that's exactly the same thing as 50 choose 6. And the question is, which system has more possible tickets? It is a trick question. Both systems have the same number. That is, choosing 6 numbers from 1 to 50, where they all have to be different, is exactly the same number of possibilities as choosing 6 numbers from 1 through 45, but you can repeat numbers in your set of choices. Okay. All right. Let's keep going. After we expand a plus b plus c plus d raised to the 7th, how many terms appear in the expansion? Okay. So the question here is not what the coefficient is. That's what we use the binomial theorem for. We did the binomial theorem on Friday. Binomial theorem tells us coefficients. But this isn't looking for the coefficients, it's just the total of number of terms. We want the total number of terms. And those terms are going to look like things like ab squared, c squared, d squared, and a to the 4th c cubed, and a d to the 6th, and a b squared d to the 4th, and so on and so forth. Combinations where the exponents add up to 7, where we can have 0 exponents. So we might have no B's and no C's in these. But that's the same thing as picking 7 letters, A, B, C, and D, when we have 4 letters to choose from. This is like picking 7 letters total when we have 4 different letters to choose from. And so that's 7 ones and 3 zeros. A 0 to transition from A to B, from B to C, and from C to D. And so that would be 10 bits in our binary strings. And so 10 choose 3. So that's a lot of terms, but that's how many different terms would appear in the expansion. Okay. All right, let's do one more. Find the number of lists of the form x1, x2, x3, x4, and x5, where each xi is a non-negative integer, and x1 plus x2 plus x3 plus x4 plus 3x5 is equal to 12. Okay. So the x5 has this restriction on it that none of the other variables have. Okay. So let's talk about the possible values for x5. Okay. X5 is special here and can be 0, 1, 2, 3, or 4. Okay. Okay, so let's talk about each of these possibilities. If x5 is 0, then I just need these 4 to add up to 12. So that's like saying that I could pick 3 in the x1s and 5 in the x2s and 1 in the x3s and 3 in the x4s. So I need to take 12 different, pick x1, x2, x3, x4 12 times, but I have 4 different to choose from. So if x5 is 0, then we would need 12 ones and 3 zeros to transition between x4 and x5, or x1 and x4. Okay. x5 is fixed at 0. We're just transitioning from x1 to x4. And so that would be 15 choose 3. If x5 is 1, then we have 3 already here, which means these only have to make up 9. So we need 9 ones and 3 zeros. And that's 12 choose 3. If x5 is equal to 2, then 3x5 makes 6, and so x1 through x4 have to make up the other 6. That would be 6 ones and 3 zeros, which is 9 choose 3. And I think you can see the pattern here. If x5 is equal to 3, then 3 times 3 is 9, and so these would have to be the other 3. So we would need 3 ones and 3 zeros, and that would be 6 choose 3. And then finally, if x5 is equal to 4, all 12 of them have already been accounted for. And so we don't need any ones or zeros here. What we're getting here is 0 ones and 3 zeros, which is like 0 choose 3. What is 0 choose 3 though? That doesn't even make any, not 0 choose 3, sorry, that's 3 choose 3. Because we still have to have the 3 0. Any number choose itself is always equal to 1. And so there's only one way of doing this. If kx5 is 4, all the other variables have to be 0. And so we end up getting, from disjoint cases here, 15 choose 3 plus 12 choose 3 plus 9 choose 3 plus 6 choose 3 plus 3 choose. Okay? So we look at the cases of what happens for x5, because that's the unusual one here. And then the other ones, we just deal with them as is. All right? Hope that helps. See you again on Friday. Take care.